Hey, it's Mr. K doing a video for AP Physics 1 and 2. I'm going to talk about some electric fields a little bit more, maybe get into some voltage, looks like we got here. What we have here is a battery, and a battery is a way to give charge to things or to provide voltage to things. You may have looked at a 9-volt battery before, or a 1.5 little AA or AAA battery, maybe a 6-volt battery, 12-volt car battery. Here we have a 9-volt battery. You've got a long line, short line. That's the way you draw it in a schematic. And I'm going to attach the long line part to over here. It's going to make this side positively charged. So usually we have that positive charge on the long side of that battery. Voltage source, whatever you want to call it. Short side is going to be negative, and down here anything attached to that's going to become negatively charged. So what that's going to cause is an electric field, because we know that positive charges have electric fields going away from them. Negative charges have electric fields going towards them, if you want to draw out the vector fields. We're going to ignore what's going on out here, but we will definitely draw what is going on between these two. Hopefully my pen works, because it was just kind of waking up on me. First time using it. Oh, look at that. Beautiful. So we should have an electric field between these two plates. And if you are in Physics 2, this is a capacitor or a capacitive capacitor plate. We'll just call it that. And we'll do one more just to make it look a little bit nicer. And so we have these electric field lines that are going away from the positive charges. They're going to go towards negative charges. And the deal between these two plates is that the electric field is actually going to be constant, which may seem a little weird, but if you think about how the field acts, as far as an equation goes, E is equal to K Q over R squared. And so as we get farther away from this side, we actually get closer to this side, and both sides are producing electric field. And so really, although we get farther away from one side, we get closer to the other side, that electric field strength stays the same. So between these two plates, we have a constant electric field. And so to talk about what's going on a little bit more, we do have a field here. Well, that's great, but we really can't do much with it until you place a charge somewhere in this field. So let's go ahead and place a positive test charge right here, and I'm going to call it a let's call it a 2 microcoulomb charge. And we always try to use micro or something small. 1 coulomb of charge is going to be a crap ton of charge. It's going to be a lot of charge. So looking at this charge, it's a positive charge. So take a guess what's going to happen. And if you're looking at the picture, we got a positive charge. We have a positively charged plate over here, this conductive plate. It's positively charged. It's attached to that positive side of the battery. We have a negative plate over here, negatively charged. If you know anything about charges, then you know that like charges will repel and opposite charges will attract. So this charge in the middle that I placed here, as soon as I place it there, it's going to have a force that points to the right. Okay, it's going to be pushed by this one, and it's going to be pulled towards this guy. So by placing this charge, it's going to have a force in that direction. Okay. Now, before I write down any numbers, we're going to do one more thing. We're going to say that the separation between these two plates, let's say it's about 0.5 meters. Okay? So there's one thing that I kind of skipped over in the very beginning, and that's the word voltage. And you may have not even noticed that voltage is a new term, that we really don't know what it is yet. Well, voltage, another word for voltage, let's write down voltage here. Another word for voltage is this thing called potential. And really it's potential difference. And so the word voltage should really be replaced with this word or term potential difference. And all that says is if you have a voltage, in this case we have 9 volts, something will happen to a charge as it goes through those 9 volts. Now that doesn't make a whole lot of sense right now, but let's turn this into an analogy of what you do know. So I'm going to turn this way, okay, and I'm going to draw just a rock, all right? And this rock is going to have a mass m. And if it has a mass m, and let's say that we have the ground down here, that's the ground, what would happen to the mass m? Well, you'd say, oh, well, the mass m, Mr. K, we know the mass m would have a force down on it, and that force would be mg. And then I'd ask you, well, how do you know that? Well, that's because of the gravitational field. You put yourself, you're on the Earth probably, you put your mass there, and you have a gravitational force. All right? Well, if you took the rock away, would anything be in this location? And, you know, a non-physics student would say, oh, no, there's nothing there. But a physics student should say, oh, well, if the rock wasn't there, you still got the gravitational field, right? In fact, the gravitational field exists all over here, and it points this way. Okay? And this gravitational field does change with distance. But for the most part, if we just talk about a problem that we just do outside in our front yard, it's pretty constant. It didn't go that far. And so if we are looking at this gravitational field, just like the electric field, if we place a mass in it, you get a force in that mass. Gravitational field's a force field. Electric field's a force field too. You just got to place the right thing in it. So if I place this rock, you get a force of mg. And if you got a force of mg, then you can fall. And if you fall a certain distance, or let's say a height, then we know that we can do some kind of force for some kind of distance. Call that sucker work, right? So you do some work. That force is mg. That h is a distance. That's potential energy. That's gravitational potential energy. So there is a gravitational potential energy change that goes from here to there. You kind of catch on? So if the rock wasn't there, h would still exist, right? So I can say, hey, there's still an h here. And if the rock's not there, we can talk about this thing that we call potential difference. And so if I placed a bigger rock at that same location, yeah, it would have more gravitational potential energy, but the potential that I placed it in was the exact same. If I placed that big rock up here, I just placed it into an area of higher potential, a location of higher potential. I could place that small rock up here, and it would be placed in an area of higher potential. Now, who has more gravitational potential energy at that point? Well, it's the big M, because gravitational potential energy deals with mass, our acceleration due to gravity, and h. How far that force can push you through, the work that it can do on you, that change in potential energy. So let's throw it back over here. If I were to place a positive charge right there, yeah, it's got a distance to go, and that distance would be something, well, whatever it is, 0.25 maybe of a meter to get down here. And so if you place the charge in a field, you should get a force. And if we have that force acting for a distance, then we should get some amount of work, right? And so what this 9 volts is this potential difference that we could give any charge here. And so it's like saying, hey, I can place any mass that I want to at these different heights, and it'll give me a different amount of potential energy. But without the masses there, there's still this difference in potential that I can talk about. All right? So over here, E is the field, Q is the charge we placed in it, D is that distance. M, G, H. G is like that field strength, H is that distance, M is that thing that you place in it. So let's go ahead and take away the thing that we're placing in. Let's take away Q. If we take away Q, we get E and D left over. And guess what that is? That's your potential difference. That's called voltage. All right? So this new term voltage, all it is talking about the potential to give a charge energy based on how much charge you place there. If I put double the charge there, if I put 4 microcoulombs there, I'd get double the amount of energy out of it. All right? So ED, the reason why I didn't want to say how strong this electric field was because I don't know. And so I can go back and say, all right, now I can figure it out. E is what I'm looking for. D, this full distance between the top and bottom, this full 9 volt difference, okay? The D is going to be 0.5. And the potential difference here is 9 volts, so I'm going to just put 9. Voltage V is going to be the joules that you can give per coulomb. All right, so that's how you can take apart that voltage unit. Voltage is joules per coulomb. Well, we're going to place a 2 microcoulomb charge here, and so all we would have to do to figure out how much energy we gave it was multiply the voltage difference times the Q that you put in there. All right, so to find out the electric field, we're going to have to divide 9 by 0.5. Well, 0.5, dividing by 0.5 is like doubling it. So our electric field is equal to 9 over 0.5. That's going to give you 18 newtons per coulomb. That is super weak. That is a small electric field. All right, but this distance is really big. So if I go back, I can say, all right, this electric field is 18 newtons per coulomb. That's actually pretty freaking weak, but that's all right. If I place a 2 microcoulomb charge right in the middle, it's got this distance to go. It's only got, it doesn't have the full distance to go. It only has half the distance to go. It's about 0.25 meters. So what has more energy? If I placed it there, if I placed it over here, or if I placed it down here? Okay, down here it's like pretty much done, right? So if I talk about placing these charges at different locations, does it matter? Yeah, it totally matters. If you place it over here, it is pushed really hard to the right. Actually, well, same strength to the right, but it has more distance to go to the right. And so if I drop a rock, if I drop this pen onto my hand from this distance, no big deal. If I were to drop this pen from my ceiling and hit my hand, it's probably still not a big deal, but it's definitely going to hurt a little bit more, right? It's got more of a distance to go. If I were to not drop the pen, but if I were to drop something much bigger, let's say like this flashlight, onto my hand from the ceiling, it's going to hurt a heck of a lot because the potential energy is higher. And so that is how the charge really matters in this case. So to recap on this video is over a concept called voltage. The voltage is just another term for a potential difference. So in other words, like how much energy you could get based upon the charge that went through this difference in potential. Okay? And so if I say 9 volts, what I mean is that there is a 9 volt difference between one side and the other for a charge to move through. And if that charge moves all the way through, then it's gone through a potential difference of that 9 volts. Well, that charge would therefore gain energy. The type of energy that it will gain is kinetic energy. And so if I were to take that difference in potential and multiply it by that charge, I would then get the amount of kinetic energy that that charge would gain. That would be in joules. All right. It's also going to cause this electric field to appear here between these two charge plates. Okay. So every time you hear voltage, you got to think about this term potential difference, this difference in energy. So if we have a 9 volt battery that provides 9 joules per 1 coulomb of charge that it affects. If we have a 500 volt voltage source that provides 500 joules per 1 coulomb of charge that it is affecting, if it goes through all 500 volts. Okay, if you have 1 million volts, then that's 1 million joules per 1 coulomb of charge. Now remember, you usually don't have a coulomb of charge. Usually it's like much smaller than like times 10 to the negative 6 microcoulombs of charge. But the more charge you have, the more energy you can transfer, and that's why it's not the voltage that's necessarily dangerous. It's going to be the amount of current, the amount of charges that flow. We'll talk about that in the next video.